which compact over time and form sedimentary rocks. As the type of sediment deposited changes, layers and layers of different types of sedimentary rock form. As the compacted organic material is now far away from any oxygen, and moving closer to hot magma, it gets more and more compressed and heated over time. This heat and pressure then cooks and transforms the organic material into what we now know as hydrocarbons. Under pressure from the huge weight of rocks above, along with the intense heat from its close proximity to magma, the transformation process starts. Over 3 million to 300 million years, if conditions are right, the carbon material in the rocks transforms into hydrocarbons. If the temperature is too high, the material will carbonize, and there will be nothing left at the end of the cooking period. Hot, but not too hot, and gas will form. Whereas, if the conditions are slightly cooler, oil will form. The cooler the cooking temperature of the materials, the thicker the oil. So how do hydrocarbons accumulate in such large amounts? Well, the answer is migration. Oil is lighter than water, so as we know it will float to the surface. Gas is lighter than oil, so the natural tendency is for hydrocarbons to migrate towards the surface of the Earth. They will continue to do this until they're stopped, and as we've seen, this requires an impermeable structural trap. These traps are formed by Earth movements and maybe domes or anticlines and faults, amongst others. Some hydrocarbons find their way to the surface, seeping out of the Earth, but most hydrocarbons become trapped in accumulation sites. So, why do hydrocarbons become trapped? This is due to layers of impermeable rocks, such as shales. These impermeable rocks act as cap rocks, preventing the hydrocarbons from further migration. As the hydrocarbons build up, they form an accumulation. The areas the hydrocarbons accumulate in are known as reservoirs. Within reservoirs, we usually find gas at the top, oil underneath, and water at the very bottom. So what is meant by porous and permeable rocks? Porosity and permeability are two of the main features that control the movement and storage of fluids in rocks and sediments. The porosity of a rock is determined by the spaces or pores between the individual grains that make up the rock. The more tightly packed these grains are, the lower the porosity of the rock. The permeability of a rock measures the ease with which fluids can flow through the rock. Most reservoir rocks are both porous and permeable, as they allow hydrocarbons to collect inside them, porosity, and to pass through them, permeability. We will now take a closer look at each of these features. A piece of sandstone. A piece of sandstone or limestone is very much like a hard sponge. If you took a domestic sponge and soaked it in water, the porosity of the sponge is the volume of water the sponge is able to soak up. Rocks bearing hydrocarbons hold the hydrocarbon fluids within the rock in the same way the sponge holds the water. The rock's porosity traps the oil inside. In sedimentary rocks, the porosity depends on grain size, the shapes of the grains, and the degree of sorting and cementation. Let's now take a closer look at permeability. It is possible for a rock to be extremely porous and yet nearly impermeable. This occurs when the pores in between the grains are not interconnected. The fluid then becomes trapped within individual pores and cannot pass through or connect to adjacent pores. Pumice or shale are examples of this type of rock. They have a high porosity, yet due to poorly interconnecting pores, some can be almost impermeable. In contrast, some sandstones can be both highly porous and highly permeable. This is due to the well-rounded sand grains, which provide unrestricted pore space between grains. The pores are free from smaller grains and are very well linked. Consequently, sandstones of this type have both high porosity and high permeability. Let's have a look at some rock types to show you an example. Igneous rocks are usually crystalline. This type of rock has almost zero porosity and permeability because there are no real gaps between the crystals. Shale is a good example of rock with high porosity and low permeability. High porosity due to the pore spaces between the individual layers of clay minerals, but low permeability because few, if any, of the pore spaces are interconnected. This also makes shale an excellent seal or cap rock for reservoirs. Sandstone, as previously mentioned, can have both high porosity and high permeability. This is the case if the individual grains are well rounded, with plenty of space between them, and the pores are well connected. Limestone will also typically have high porosity and high permeability. However, unlike sandstone, it is also very soluble, meaning it can dissolve in water much more easily than other types of rock. This is yet another way limestone achieves high permeability and porosity. Water can expand the cracks and fractures already within the rock.